The purpose of this video is to learn how to blink an Arduino LED, but this is going to go beyond the example that you get with the Arduino compiler called Blink. I'll show you ways to do things that will save memory, that will give one a better idea of how the hardware operates, and so forth. So let's take a look at blinking an LED from a hardware programmer's point of view. Because the Arduino is oriented towards electronics and electronics control, it doesn't hurt to review what exactly is an Arduino. In reality, it's a microcontroller. The most basic version is the ATmega168 I will use as an example. The following code I'm going to present after this should work on most of them as far as I know. But what does a microcontroller consist of besides ground and power pins? It consists of ports. These are 8-bit devices, so you're going to expect these to be mostly 8-bit ports, known as I/O ports. They consist of an 8-bit latch and an 8-bit data direction register that tells the internal electronics if a particular pin is an input or an output. On this one, there are 3 ports. What you would call your transmit and receive digital pin through digital pin 2 through digital pin 7 is port D, also known as port PD0 through PD7. That's 8 bits. Normally you don't really use PD0 or 1 because that's your transmit and receive for your serial. You can if you want to give that up. Your next port, of course, is port C, which consists of PC0 through PC6. PC6 is used as your reset, but PC0 through 5 are your analog inputs. They can also be programmed as outputs. For most of my little demos here on my gadget board, I use digital pin 2 and digital pin 3, which is PD2, and PD3 as inputs. That is, I go to the associated data direction register and make sure that they are set to 0. That's your pin mode, pin 2, comma, low, and pin mode 3, comma, input. We'll explain that a little more later. The LED that is connected in this is actually connected to PB1. If you look at port B, you have access to port B0 through port B5. Port B5 being digital pin 13, port B0 being digital pin 8, and we shall be using port B1, which is digital pin 15. I have to make this an output. So I will have to, in the corresponding port B data direction register, I have to put a binary 1, which is a pin mode, comma, 9, comma, high, or 1, or whatever you want to do. Keep this in mind. You don't have to remember this entirely. But whatever Arduino you are using, at least look up the device's spec sheet. Try to get familiar with what you're really dealing with. If we go into the Arduino as it first comes up, it has a sample program called Blink, where you're just going to blink the LED that's normally connected to digital pin 13. Let's note for starts, if we have just an empty setup and an empty loop with nothing in it at all, that's 450 bytes. An empty setup and empty loop is 450 bytes. It will compile up It uses 450 bytes and does absolutely nothing. But this is the underlying structure for the program. When I compile the Blink program, it comes up to 1030 bytes, take away 450. I've used 580 bytes to simply blink an LED. What does it consist of? Setup consists of simply pin mode 13 output. The rest of it is just a digital write. 13 turns on the LED, you wait 1 second, then you digital write a low, turns it off, you wait a second. So you only got, 3 commands: pin mode, digital write, and delay. What I'm going to review through is a better way to blink an LED, looking at it from a software integrated with a hardware perspective. This here completely isolates you mentally from anything to do with the hardware. If you want to understand how to connect sensors and other types of hardware, you're going to have to start looking at these programming from a hardware person's point of view. All right, we're here at my Arduino Sketch, and just to make myself a note, this is what the port would be written as in binary, and just to keep this in mind, PP7 through PP0. That's because I'm using digital pin 9 as designated as LED1. Digital pin 9 is port pin PB1. Written in binary, here is PB0, here is PB7. This just lists what port B pin is connected to what digital pin. All right, as I said, I defined LED1 as digital pin 9, DP9 or PB1. That's the LED I was blinking in the video. All right, let's look at, I also wrote to demonstrate a little way to save memory and increase processor speed when it's executing programs. I wrote my own millisecond delay, which is nothing but a for loop. And I used delay microseconds 1000. 1000 microseconds is 1 millisecond. Why would I do this? For a lot of reasons. If you use delay milliseconds, you're not tying up your interrupts. If you are trying to use an interrupt service routine and you call delay, it won't work, because delay in the Arduino, the delay function uses interrupts, and you can't use it from an interrupt service routine, because when you get an interrupt, it disables the interrupts until you leave that interrupt service routine. I'll discuss that elsewhere. Nonetheless, using an unsigned integer, let's look at a little bit at integers so you would understand. Okay, the routine I wrote is x times 1 millisecond delay. For one reason, my delay routine uses 64 bytes. The delay routine that Arduino uses 180 bytes. I'm doing the same thing with a third of the memory space. An unsigned integer uses 2 bytes. And to figure out how big a number 2 bytes is, you take 2 to the 16th power minus 1. So I can, using an unsigned integer, I can have 65,535 milliseconds. If I want to use an unsigned long, that uses 4 bytes, which is 2 to the 32nd power minus 1. You're looking at 4.3 billion milliseconds. So I think, well, I'm just going to say it. My delay, which the code for it you see here, That's all there is to it. Uses a whopping 64 bytes. And if you decide to use an unsigned long, you could have 4.3 billion millisecond delays, and it'll be very accurate. All right, let's look as a quick review of our data direction and hardware registers. DDR, or data direction register, if you put a binary 0 in the corresponding bit, it makes the output pin an input. If you put a binary 1, the corresponding I/O pin becomes an output. In the port B, which is also the data register, or port B data register, a binary 0 produces an output of 0 volts. A binary 1 produces an output of 5 volts. I'm assuming you're using a normal 5-volt system. Moving on down a bit. This is the binary representation of the port. This is PB7. This is PB0. The LED that I'm connecting, that you saw at the beginning of this, is at PB1. PB1 is digital pin 9. This represents digital pin 8, digital pin 9, digital pin 10, digital pin 11, digital pin 12, and digital pin 13. These two here you cannot use anyway because they're connected to the crystal. So here's the listing here. I like to list this stuff up here as notes or reminders. For this discussion, I also created my own delay routine, which is highlighted down here, which I call my delay. It consists of nothing but a for loop, and I'm going to use delay microseconds 1000. 1000 microseconds being what? 1 millisecond. So it's x times 1 millisecond. The difference between mine and the delay that is normally used in Arduino, the Arduino delay uses 180 bytes. Mine uses 64. The Arduino delay function ties up the interrupts. That is, if you're doing something with your interrupt routines, delay doesn't work. Mine works whether it's interrupt routines or regular routines, and still only uses 64 bytes. Noting something about numbers. An unsigned integer uses 2 bytes. Unsigned means it can only be used as positive integers, no negatives allowed, but you don't send a negative integer to this delay routine. That makes no sense. How big is the numbers you can use? 2 to the 16th power minus 1. Just using an unsigned int, you can delay 65,535 milliseconds. If you want to use an unsigned long, uses 4 bytes. That's 2 to the 32nd power minus 1, about 4.3 billion, that's with a B, billion milliseconds. That should be big enough for anything, it would seem. So, again, my delay I'll be using as a comparison to to Arduino's delay. And I have defined LED1 as digital pin 9, which, by the way, is connected to PB1 on the ports on the Arduino Mega 168. All right, up here I've defined LED0 as digital pin 8. LED1 is digital pin 9. LED2 is digital pin 10. We have to set up our data direction registers first. In this case, since I'm using port B, PB0, 1, and 2, The most efficient coding way to do this is to simply OR whatever you want to set up with data direction port B and store it there. This bit represents PB0, or, well, digital pin 8, digital pin 9, and digital pin 10. If I want to set all three of them to outputs, it's a binary 7. This is what it is written in binary. Some people complain, well, you don't need to OR it. I'm going to argue that you do. I'm not going that deep into ports. Or you can set it directly for number 7. These are just the binary versions of 7. You can do that. The best way to do it is to OR a binary 7 to make those three outputs. We don't normally do that because most people have problems dealing mentally with hardware ports. But if you want to learn your ports, this is the way you can go. I have a separate video and web page on that. I'm not going into it any further. Let's note something. There are constants that are defined in the Arduino compiler. Pin mode. All right, let's look at this. High equals 1 equals output. Low equals 0 equals input. I can use high, 1, and output interchangeably. I can use low, 0, and input interchangeably. Now remember up here I used OR 7 with data direction port B, and I set all three output bits to output at one time. But let's go down here to pin mode. Pin mode LED 0 output. That used 180 bytes. What does it do? First of all, it knows that LED 0 is digital pin 8. It's going to go through a table, look up pin, it'll look up pin B, PB0, and it interprets an output as a binary 1 and puts a binary 1 in the data direction port that corresponds to PB0. It's an awful long way around, and you used 180 bytes. So this is what, and note when you see this double slash line, these are comments. It's not seen by the compiler. So what's going to happen if I have to set all three I/O ports? I got to do it I got to use pin mode 3 times, but each subsequent use of pin mode, it cost me 180 bytes the first time, 8 bytes each additional time I use it. And so I had to use 196 bytes to do what I could do up here in 2 bytes. Again, it's going to be up to you what you want to do. Let's move down a little bit more. All right, let's just argue. You notice down here in this statement, I have replaced the word output with 1. Remember I told you back in the hardware setup, you put a 1 in the corresponding data direction register bit, it makes it an output. Well, output is a 1. Or I could even put high in it, which is also interpreted as a binary 1. Any of them will work. So using direct port commands is the most efficient way to set up hardware, but it takes a higher degree of learning complexity to catch hold of it. If you want to make really high-speed hardware interfaces, this is what you need to do. Most people are going to use pin mode. Pin mode is slow, inefficient, but it's easy to use. The only thing you have to remember is, at worst, putting in the correct digital pin, 9, 10, or 11, and setting it for output. The compiler does all the rest. The first time you use pin mode, it's going to cost you 180 bytes of memory. Each additional use is going to be 8 more bytes. And remember once again that high, output, and binary 1 are constants within the Arduino compiler. They all mean the same thing. Low, 0, and input all mean the same thing. Let's move down the sketch. First, the next thing I've done is I've defined a variable num equals 0. I made it a byte. A byte is an 8-bit unsigned integer. This is an integer, no fractions allowed, sorry. You can put a value from 0 to 255. What do we need to do mentally to blink an LED? Well, we're going to turn the LED on. We're going to wait. We're going to turn the LED, excuse my spelling, turn the LED off, and we're going to wait. Then we're going to repeat the cycle. How we do that determines how much memory we are going to use. We can go the example blink that Arduino comes with, or we can do a little bit of thinking and maybe get the amount of the 580 bytes down. All right, now we're down here to loop. We're finally going to blink an LED. Remember, we defined the variable num is equal to 0. There's 2 ways to flip the state from a 0 to 1 with num. You can XOR with 1 directly. That's the little hat symbol on your keyboard. Num XOR 1 equals num. This is really the same thing as num equals not num. A not function is the same thing as an XOR function. Or the most efficient way to do it, but it might be more confusing to you, is use a port command. You XOR port B with a binary 2. This, remember, that represents digital pin 8, digital pin 9. I'm just blinking the LED on digital pin 9. You could go this way and use 8 bytes. By doing this, you don't even need the variable num at all. You can eliminate this, the variable, the works. So let's just argue we're going to do it the simplest way for everybody. We're going to eliminate that. We're going to eliminate this. We're just going to use num equals num, 14 bytes. All right, we're going to take num and we're going to do a digital write of num to the output port. Okay, assuming it came in at 0, it's now a 1. Digital pin 9 is LED 1. This statement here lights up my LED. I could, for instance, do this. Eliminate that. And use this statement. And you see it's LED 1, comma, num equals not num. You can actually put that statement right here within the digital write. The compiler will look at it. It will do this first, then do the rest of it. But it doesn't save us a whole, but it saves us really absolutely nothing. So let's keep it sort of simple. All right, now we come to delay. My delay uses 64 bytes. The Arduino delay uses 500 bytes. Okay, so we're going to use the num. We're going to use the digital write. Now all we need is to choose a delay. I'm going to use my delay. It's going to delay 500 milliseconds. So now that I used num in the way that I did, I do not need any of the rest of this. And so, what did I have? Okay, the first time I went around, 0 became 1. I wrote 1 to the LED. LED lights up. I wait 500 milliseconds. The loop comes back around. This time it's 1 ends up equaling 0, digital write. Num again turns the LED off, and my delay. It just repeats these 3 simple commands over and over. Did save quite a bit depending on what you want to do up here in setup. So everybody can be as happy as possible with the least complexity. We used 180 bytes with pin mode, 14 bytes with the not num routine, 268 bytes with digital write, and 64 bytes with this. As I just showed you, there's all kinds of combinations to do this. So this is better in a lot of ways than the original, but I could use port commands with my delay and do, instead of this is going to come out to be about 900 bytes instead of 1030. If I use port commands in my delay, I could blink an LED with 74 bytes. So that's just an introduction to how you can look at this programming. The closer you get to the hardware, the more efficient it is. Thanks for listening, and visit my website at www.bristolwatch.com.